All right, welcome back. Let's analyze something here, but very little about electricity. We'll start with this first diagram over here. This is our source. It's a 9-volt battery. This is a positive terminal. So current will flow from the positive terminal through a resistor. This resistor is a 1 kilo ohm or 1000 ohm resistor. Current will flow into the LED, and this is the anode. Through the LED to the cathode, current will continue to flow to the second LED through the anode to the cathode. It will light it up. Current will continue to flow to the third LED to the cathode, and current will flow through the ammeter. This is a multimeter. Right now it is set at amperage. We measure the current, and it will flow to the negative terminal through the ammeter, and will flow back to the negative terminal of a battery, and thus completing the circuit. So if we simulate this, we'll see that the LEDs light up. The 3 LEDs light up, and the total current in the circuit, total current in this circuit in series is 3.31 milliamperes. So about 3,000ths of an ampere. That's 3 divided by 1,000, right? So this is very small amount of current in the circuit. Now we know the LED light bulbs, they will have a voltage drop across the LED light bulbs is about 2 amperes, 2 volts. So out of these 9 volts, about 2 volts will be eaten by this LED, about 2 volts will be eaten by this LED, and about 2 volts will be eaten by this LED. And you will say, but if 2 volts is eating by this LED, 2 by this, and 2 by this, that will be 6 volts. Where is the 3 volts? The 3 volts, extra 3 volts will be eaten by this resistor. And in fact, voltage as a formula, if you know, voltage as a formula equals current intensity, which is the current in the circuit 3.31 times the resistance. And we say this resistance is 1000 ohm. In fact, if you multiply 1000 ohms by 3.31 milliamperes, I times R, we'll have about 3.31 volts. So this is where the other voltage, the remaining voltage is eaten by this. From this formula, we can see that. But what I am interested in is the brightness of our LEDs. The brightness of our LEDs is what we want to focus on today. Now, I'll tell you something. Now, you see, what controls the brightness of your LED is how much energy is being dissipated here as heat to light up this thing. And that energy, we need to know the power that passes through the LEDs. And to calculate that power, you have to say, what is the amount of electrons that are flowing through the LEDs? And what tells us the amount of electron per second is the current intensity. And then now we also need to know the voltage drop across the LED, which is that 2 volts. So we multiply. So if the voltage drop across, it means that is the pressure that is pushing these electrons through it. But the voltage drop here is fixed. It's around 2 volts. So we'll do the current intensity, which is 3.31 millivolts. We multiply by the 2 volts of voltage across here. It will be 2 times 3.31. That will be about 6.62 milliwatts, since this is in milliamperes. So it will be milliwatts. So just 6.62 milliwatts is the power, and that power tells us what the brightness will be. Now, if you keep this circuit open for 1 hour, we will take that power, multiply by 3,600 seconds in 1 hour to just know the energy that each LED will consume in 1 hour. So from current intensity to resistance to voltage to power to energy, those are the concepts that we can learn from electrical circuit. Of course, that energy is called electrical energy. Now, this is this circuit. So we got just this voltage. Now, do we want to see this circuit? How we can draw it in our electrical class? This is a circuit right here. All right? This is a circuit right here. Let me, oh my God. Oh my God. I've messed things up. Okay, let me bring everything back. I had a situation where this was like this. Okay, like this. Okay, let me bring everything back. So this is the circuit. So the circuit says I have a 1 cell battery. This shorter end means the negative terminal. This longer end means the positive terminal. So this is how we write a battery, or we draw a battery in our circuit. And we label there 9 volts, right? And then now current will come from this positive terminal, will go through our resistor. So this is how we indicate a resistor in a circuit. Sometimes we can use a rectangle bar, but in this case we use these zigzag lines. Yeah, so this is 1 kilo ohms or 1,000 ohms of resistance. Okay, the bigger the resistance, the in series, the bigger the resistance, the more voltage from here that this thing will eat up. So if we want it to eat up more of this, we increase the resistance. If we want to eat up less of this, we reduce the resistance. Now this volts is the pressure that is pushing electrons around the circuit. And the pressure of electrons that will get into the, that will go through these 3 LEDs in series, that pressure is the same. The electron speed will be the same because it's in series, right? So the current intensity will be the same. But that pressure here, this will only consume 2 volts of that pressure, 2 volts of that pressure, 2 volts of that pressure, 6 volts. So we cannot build this circuit without this resistor because we have a 9-volt battery. If we had an exactly 6-volt battery, can it go? It would also not go. It will also not go for the purpose of the pressure pushing. Yes, it will be 6 volts, but we don't have anything to resist it. So it will make that electrons that will be coming out so fast. So we have to also reduce that pressure, and that will be the current. So we need a resistance, because the resistance around these, the resistance through these LEDs, these 3 LEDs. So this is how we represent a load. So a load is the reason why we have a circuit. We have a source, and then we should have loads. So this source is to power these 3 loads. And these 3 loads, their resistance of the LEDs is about 0. All right, so they don't resist current. So that's why we need a resistor in the circuit to help us reduce the current intensity, right? To help us reduce the current intensity. So because the current that should pass through here should be less than 20 milliamperes. Now you see this circuit, I will go and reduce this 1 kilo ohms to about 0, right? So I'm going to put 0 here. I'm going to put 0. You see what's going to happen? I'm going to put 0. You see? this blows off, blows off, blows off, and here we have 146 milliamperes. And this current speed, this is the speed of the electrons coming through here. They will just burn the wire that is inside here. That makes it glow. It will burn it because that's too fast. The speed of the electrons is too fast. So current intensity, it shows like the total amount of electrons that are coming there, the speed coming there per unit time, the total amount of electrons coming there. So that this is kind of the speed or the current of electrons. Your electrons are your charge. Okay. Now, so it's too high. The speed is too high, so it destroyed the metals inside. So we need to reduce the speed. So we go back to this resistor. That's why we made it 1 kilo ohms. 1 kilo ohms. Okay. So, and we have this. Now, if we were to increase this, decrease this value further, then what will happen to the brightness? I think because it's 1 kilo ohms, so the current is this little. If we were to increase it, decrease it, the current will rise. So let's try to decrease this to 500. But you have to remember, you have to change kilo ohm to ohms. Now it's 500 ohms, you see, our current has doubled from 3.31 to 6.33. It has at least doubled. The resistance here is negligible, but I think it's still a little, probably like 2 ohms, 3 ohms, like that. So this is not 3.31 times 2, inside give us 6.62, but it's 3.33. So it's almost double. I think we can actually say it's double. Now, if we reduce this further again by half, let's say we go from 500 to 250. Let's see what we have, 500 to 250. Okay, you see, we've doubled again. We've doubled from, where were we? We were at 6.33. We've gone to 11.9. That's closer to 12. So that's almost double, right? And then if we go from 250 to 125, we reduce again by half to 125. What will happen? You see, we took the 11 point something, we're going almost 21 point something. You see, that's also double. But here we have a warning. If we read this warning closely, it says, read the warning here, it says, current through the LED is 21.6 milliamperes, while the recommended maximum is 20 milliamperes. So here we have 21. It is not allowed because even though the bulbs are brighter, you see, much brighter because the current intensity is higher. And again, what controls the brightness is the power. The energy that will be released here is related to the power. Power times the total number of the time that the circuit is on gives the energy, so total energy. So power is just your energy per unit time, right? So power here means energy per second. So the higher the power, it means the more energy, per second we have there, and that will brighten it up. All right. So always keep this idea of power. That's why on light bulbs, the bulbs that we have in our homes, we see it will say 3 watts, 4 watts, 5 watts. Okay. So again, the higher the wattage, the brighter the light bulb is. So don't go and buy a light bulb of 5 watts and you say, oh, it's cheaper. If you want the light bulb to be brighter, if you have a very big room, then you need a light bulb of a higher wattage, right? It means they will be brighter. It will be brighter. Okay, so that's just the meaning of these watts. You see on light bulbs, we have watts. Okay. Okay, so we have a problem. We have to make sure that we reduce this under 20. It's not bad here. It did not blow it up like the case where we have, if we were to take it to 0, it will blow it up. So this 21.6 is not terrible. It's not terribly bad. But the issue is, it's also not the best. So it will kind of like reduce the lifespan or how long this thing can be good, right? So even though it will not blow off in the beginning, but maybe after like 2 months, you'll have to change it. So you have to respect this 20 milliamperes. So you go to the resistance here and we increase it to about 150. Let's see. We increase it to 150 and we're good. You see, it is 18.5. 18.5, is it also better? Is 18.5 better? Yes, it's less than 20. But there's also a small issue, a very little issue. It is too close to that 20, because sometimes things like temperature, things like humidity, just environmental condition, they can affect our circuits, right? And you say, but teacher, why would temperature or the humidity affect our circuits? Yeah, even people, you see, in cold weather, hot weather, you have moods, right? So environmental conditions are very normal to affect things, right? So don't be too close to that 20. So around 15 is much better. So, but we'll get back to 1 kilo ohms because we want to use 1 kilo ohms across the board and see which to compare brightness in different ways of connecting three light bulbs. So this is in series and the brightness is very poor. Now let's go to the second case, this case here. Look. All right, so bear with me. Let's see. So in this case, we connect the light bulbs in parallel. So we call this in parallel, you see. So this one is in series, you see, straight current goes here, the same current goes through, the same current goes through. But here, the current leaves here, goes through the ammeter. We can measure the total current in the system first. And then, so we see here the 7.12. In this case, where we have these light bulbs in parallel, we have more current in the circuit than in this case. Is this also 1 kilo ohms? Let's check it out. Let's check this and see that is the same, 1 kilo ohms. Right, like this also 1 kilo ohms. So, but this is in the parent part of the circuit. So this is a resistor here, 1 kilo ohms. So current comes here, pass through our ammeter, we measure our general current. But when current comes at this junction here, current is going to split two ways. Part is going to go down here, part is going to go here. It comes to the next junction, it splits also two ways. Part is going to go here, go through this one, come here, unites with the part of the current that passes here, and then now we have both current that entered here is the current that is leaving here. Then it comes here, the current that went down here and the current that is coming this way unites, and we see have the general current in this path going back into the battery. And then the same thing repeats like that. So the current that we have in these branches are less than the current we have in this parent part. In fact, the current in the parent path is going to split three ways, and then unites back again down this way and onto. Now, will this improve our brightness? Yes. If you can see, this is a little bit brighter than this one, a little twice as bright as this one. Okay. Now let's go down to the last scenario, the last case. So, but anyways, we still didn't improve it. We still did not improve it that much. All right. Now let's go to the last case. Now this is the last case. Now in our last case, what do we see? We still have our battery here, and we pass current flows out of the battery. Once we have a circuit, current flows out of the battery into the ammeter. So we measure the general current speed, the current intensity, what we call current intensity, I, in the circuit, the speed of the electrons, because this our voltage is the pressure that is pushing electrons through the circuit. So this will measure the speed of the electrons. And then we come here, we split the current in three ways, but when the current goes through the light bulb, it passes through the resistor. So each light bulb has a resistor in this parallel circuit. Each light bulb gets its resistor. Oh, I see there's one thing we didn't do. When we're drawing our schematics, we had to put X. Yeah, in this round here, it shows that is the load. All right, it shows that is the load. And now, current, so each LED got its own resistance. And then you see here, this LED resistor here, this LED resistor here, this LED resistor, as in this circuit, right? And now what do we need to do? Okay, so what do we need to do here? We see that it's much brighter and the current is 21.1 milliamperes. It's actually above the 20. So drastically it has increased the wattage, because we have to take this and multiply it by the two. This is a general current in the circuit. but the current that is flowing through each of these have to be split by 3. 21 point this divided by 3. Yeah, so that's why these two brightness, we didn't improve the brightness that much, but I think it is much better. The general current, yeah, the general current is this, but through each of these circuit, it's still gonna split the current by 3, since we have the same conditions all through. So 21. Yeah, so this brightness and this brightness, which one is better? But in general, we have improved the brightness slightly over here. I can see this is slightly brighter than this, but not that much. Yeah. So what happens in our houses? In our houses, we don't connect bulbs like this. In our houses, we pull the electricity from the mains. I'm going to show you how we do it. It's very easy the way we connect electricity in our houses, okay? So in our houses, we pull electricity from the mains. If this is your electrical meter, this will be the wire. So okay, so this is the red wire, and then we have the black wire. Okay, so it's and all this is inside one parent wire cable. Is all one inside one covering. It's so cool. Yeah, so this is all inside one covering. So at the end, when you get to the place where you have to put your bulbs, so it's like you just pick, yeah, you just pick the red from here, and then pick the black from here, pick the black from here, and then just connect your, yeah, and then you just connect your bulb here. Yeah, you just connect your bulb here. So it's so easy to wire a house. You go to the next one, pick the red again, and then pick the black again. Yeah, and then wire the house. So this is in parallel. So you see, they are in parallel. Yeah, they're in parallel. So meaning that if the current that is coming, the current that is coming in this main line, that current is split into 2. Part of the current goes there, the remaining part continues, and then part of it goes there. It's also your current is split. The current is split, right? So, and you see that if we split current that way, we improve the brightness in the system. We improve the brightness in the system, and we don't have this 3.31. We instead have something like this 7.12. And in this case, even though in the parent circuit, no, excellent. In this case, this 7.12 gets here and it is split. It is split, okay? But in this case, 21 point this gets here, it is split. It's split, so we get 7, about 7 each. But here, this 7.12 gets split. Here, we instead get less. So that's why this case, putting this resistor R here does not help that much. We have to put each should carry its own resistor like this. So the light bulb in our house is so special that it carries its resistor inside the bulb. It carries its resistor inside the bulb. So we don't have to really worry about buying a resistor to build to connect our homes. So this light bulb has its resistor there. So this is, you connect to the meter, and at the end, link these two back so that we make a complete circuit. And we come back to where the government gave us this, and we give it back to the government. So it's very easy to connect, to wire the homes. Yeah, so at least we get the concept. And let's see, follow us for more on electricity. And leave your comments. If you want me to really take it slowly next time, I'm going to take it slowly next time, probably start from a simple circuit. But again, remember the concepts we have to explain is that if I have 9 volts and I have components like this, they will eat 2 volts, 6 volts. So I will need a resistor for two reasons: to eat part of what is left, and also to reduce the speed of the current in the circuit. Why? Because we have components that don't need very high speed of current. If the current speed is too high, they will blow off. So the resistor in a circuit plays two roles. One, if you have a battery that has more than the voltage that we need, this resistor will eat part of that pressure. All right, that's number one. And the resistor will help to also reduce the current intensity, especially if the light bulbs themselves don't carry internal resistance. Yeah, we need to resist that high pressure that is pushing electrons around the circuit, so that we get to a level where we have just the right amount of speed of electrons that are going through the circuit, and this flow of electrons is what we call electricity. Okay, we'll stop here for now. Don't want this class to be too long, but we'll have a series of classes where we'll go step by step, so you can follow that on a playlist of electricity in our Moriri Enterprises channel. All right, so please do us a favor. Don't forget to subscribe and like please, and leave comment. Tell us what you want us to treat next time. I'm an engineer, and any topic is okay, from the arts to just STEAM: science, technology, engineering, arts, and mathematics. Whatever you want me to treat, I'll be able to do some research and treat it with a special touch. All right, especially with technology. Okay. So thank you. We appreciate it. We appreciate that you're following us and you're watching.